Hello everyone, I'm Shuya, an early-stage researcher in the TERAOPTICS, pursuing my PhD degree right now under supervision of Professor Andreas Stur in the Department of Optoelectronics at University of Duisburg-Essen. In this online lecture, we would like to give you an overview of the key components in the terahertz wave generation and modulations. First, please let me start with introduction of terahertz waves. Terahertz waves are one of the electromagnetic waves such as radio waves, infrared, visible light, and X-rays. Generally, the frequency range of the terahertz waves is from 0.1 terahertz to 10 terahertz, which corresponds to the wavelengths from 3 mm to 30 micrometer. Given that the terahertz waves are located in the intermediate region between the radio and light waves, they have been intensely studied from both the electronics and the photonics approaches. However, developing the technology to yield high-power terahertz wave generation has been extremely difficult with both approaches. The figure in the middle shows the output power of the single semiconductor on-chip terahertz sources as a function of generated frequency. As you can see, there is no terahertz on-chip source with more than 10 dBm at 1 terahertz, and the terahertz region have remained for a long time without the industrial utilization. Therefore, it has been called terahertz gap. Nowadays, this terahertz gap is being bridged by the development of various state-of-the-art devices and techniques enhancing the terahertz output power at room temperature. Next, I'm going to explain you the feature of electronics and photonics-based terahertz wave generations. Use of terahertz transistors and diodes has several advantages, such as high efficiency in energy and size, and high effectiveness in cost. However, each type of electronic devices has limited in the highest cutoff frequency. This is because the transit time through the electronic devices determine their operational speeds. To realize a higher frequency fundamental oscillation, advanced device processing technology to make finer structures are required, which would be more and more challenging in the future. In our best knowledge, resonant tunneling diodes, RTDs, utilizing the tunneling effect through the very thin quantum well layers, have shown the highest fundamental oscillation frequency at 1.98 terahertz. Regardless, the electronic devices are limited in narrow operational bandwidths, which can be a disadvantage for realizing ultra-wideband terahertz applications. In another electronic approach, frequency multiplying is a commonly used technique to generate high-frequency terahertz signals. By doubling or tripling the frequency of local oscillator signals and using additional amplifiers, high power and high frequency operation is in relatively broadband frequency range is possible. However, noise accumulates as the number of multiplying or amplifying steps increases. That's not ideal for terahertz applications, which require ultra-low noise terahertz sources. Besides, cascaded electronic systems introduce large power consumption that cannot be ignored. On the contrast, photonics-based technologies and techniques have advantages in terms of the noise and the operational frequency range. First, I will explain about the photomixing technique, which is a key for terahertz continuous wave generation based on photonics technologies. As you can see in this slide, two optical signals with different wavelengths colored by blue and red are generated by a pair of wavelengths tunable laser diodes. These optical signals are mixed and down-converted to generate terahertz waves colored by purple. As the generated frequency corresponds to the differential frequency of the two optical frequencies, it can be easily tuned by adjusting one optical wavelength from the laser diode. For this purpose, unit-traveling carrier photodiodes, UTC-PDs, have been of significant interest as high-speed efficient photomixers in the terahertz band. The photomixing using the UTC-PDs has demonstrated the operation beyond 4 terahertz and milliwatt level output power over 300 gigahertz. In addition, similar to the photomixing technique, it is reported that quantum cascade laser QCL and photoconductive antenna PCA can also be employed for differential frequency generation, and they have also great promise as a method for generating terahertz continuous wave recently. The quantum cascade laser QCL is very attractive for high output power operation. The QCLs uses subband transition in quantum wave rather than spontaneous emission as in conventional lasers. Hence, the operational frequency can be selected by adjusting the band gaps. Moreover, by cascading the quantum waves and the induction parts periodically, a much higher output power compared to the other terahertz sources is reachable. However, there's one thing limiting the use cases of the QCLs, which is low temperature operation. Operation at room temperature has been achieved recently, but still the output power is low at room temperature, and additional cooling system is necessary for high power operation for now. Finally, let me introduce photoconductive antenna, PCA. When two electrodes of the PCA are DC biased and irradiated with femtosecond laser pulse, a transient photocurrent is produced between the electrodes, resulting in a terahertz pulse generation. This ultra-short pulse has an ultra-broadband terahertz spectrum. To our best knowledge, ultra-broadband operation up to 10 terahertz has been reported so far. Despite its promise, the output power is relatively lower than that of the other terahertz sources because of the lower optical to terahertz conversion efficiency. To achieve higher output power, higher DC bias is required, which is another challenge. That's all for my part. Thank you for listening to Chapter 1. I hope to see you again in another video. See you later.